Okay, so I'm going to pick up where we left off last time, and I want to talk about a bond between two atoms versus a lone pair. Now, in terms of, we're going to call it bond distortion. Okay, bond distortion Okay, the first thing is if we were looking at methane, so we have now that's a tetrahedron. And if those are all hydrogens like methane, this angle is 109.5 for a pure tetrahedral. However, when you differ from it having atoms that have different electronegativity spread out, that angle is no longer going to be 105 or 109.5. It's going to be something else. For example, if you had okay, that CF bond is going to be shorter. And that shorter bond means the electron is going to repulse more. So the angle is going to be greater than 109.5. So the distortion of the angle is going to be more. Excuse me, it's less than 109. Because what's going to happen is, as this gets closer, it's going to push these bonds closer together. Because these electrons are going to want to get away from these bonding electrons. Okay. So you have the perfect angle, like with trigonal planar, is going to be 120, assuming they're all the same atom. If they're not the same atom, that 120 becomes 122 or 118, something different. Okay, so when an atom comes in closer, it pushes the other bonds closer together. If this is longer, it's going to allow these to spread out more. Okay, so that's one kind of bond distortion. Does that make sense? Yeah.
So for the second one, where it would be less than the 109 and the hydrogens get closer, what if it wasn't 3 hydrogens at the bottom, but like 2 hydrogens and then another atom? Would the different ones still want to go away?
You still want to, when something, hold that thought for a second, because I want to talk about electron pair.
Okay.
Electron pair is even shorter.
Okay.
And That's a good question, though, and then it gets complicated. But if they're all the same, you know, HHH, it's, yeah. All right, so the other one is if now, when I say electron groups, depending on what table you're looking at, sometimes they refer to that as electron domains. Now, electron pairs that are non-bonding are particularly close because there's no other atom pulling the electrons back. They're just all being attracted to the one central atom. So let's look at ammonia. Now look at the difference between these two. When you have, like if this is a central atom, this is a bonding atom, this electron cloud is kind of looks like this, kind of spread out. But when there's no atom over here, the lone pair electron cloud is kind of squished up against the central atom. And because of that, it takes up a lot more room. And that means that the effect of these electrons on the other atom bonds is going to be more pronounced. So keep that in mind about electron pairs. They are just the extreme version of electronegativity. It just sucks it all in. You get the most extreme distortion with electron pairs. So if we look at this guy here now. Now this is a tetrahedral. So we normally think of the angle as being 109.5, assuming all those were equal, like we did with methane. But because we have an electron pair there that's not bonded to anything, its influence is going to be much more appreciated. Okay, so we've got we have some elongated electron sharing here. It'll look like this. But the electron pair, notice, is short and squat. In other words, the density of the electrons now are closer to the central atom. Hence, the effect of the electron lone pair is going to start reacting on these. It's going to be repulsing those nitrogen-hydrogen bonds away from the nucleus. So now that angle is less than 109.5. Now, in the case of nitrogen, it happens to be 107. It really doesn't matter that you know it's 107. The important part of this is that it's less than 109.5 and why it's less than 109.5. The why part's really important, okay? So electron pair is closer than a normal NH here, and its influence, therefore, is greater on repulsing these electrons here, pushing them closer together. So what do you think the effect would be If we had, instead of one electron pair, what if we had two? What do you think the bond angle there will be? Using the reasoning on NH3.
Plus.
Yes, even more so. Instead of one, we've got two. So those are going to shove it together even more. Now I'm going to use double less thans, meaning it's more than the one. It happens to be 104.5, but that number 104.5 is important. What's the important part here is why it's so much less, okay? I want everyone to understand that. The why here is the part I'm interested in you knowing why, okay? Because they're shorter end, the influence is more. So the electrons in those bonds, the NH bonds or OH bonds are repulsed even more and pushed together more. So these are simple examples. If this was a H and an N, for example, it would complicate things. But in the pure sense, that's what I want you to know. And the why part. Okay, does this make sense? Okay, so bond distortion is really a big deal. Okay, what happens now if we have more than 4 electron groups? What if we have 5 and 6? Okay, the concepts we talked about are going to be the same, just more complicated because there's more combinations you can come up with in the molecular geometry part. The electronic geometry is going to be similar conceptually. There's just more combinations we can come up with. Okay, now the important thing when you get to 5 and 6 are there's 2 kinds of positions that are not equal. There's equatorial ones that go around the equator of the central atom, and polar ones, which are on the poles of the central atom. And those are not equal positions. Okay. Now, when we have 5 electron groups, 5 electron domains, this is what the central atom is going to look like. Now, notice that if you have a lone pair, where does it go? Does it go equatorially or polarly? It's going to go where there's the most room, because when the lone pair comes in, remember it's bigger. So it's going to go in the place that's got the biggest space. In the case of the trigonal bipyramidal, where there's 2 pyramids stuck together, the biggest space is going to be equatorially as opposed to polar. So that would be what the electronic, covering up the atoms, that would be the electronic geometry. The polar geometry in this case is going to look like this, and it's called seesaw. And some of these names make sense and some of them are, in my opinion, don't make sense. But you have to differentiate each different version. And it's going to depend on how many lone pairs and how many bonding atoms you've got. It'll depend on what the final molecular geometry looks like. But the most important thing, when you have 5 electron groups, the equatorial area is where the lone pair is going to go first. Okay, boom. Now we're going to find when we have 6, we have an octagonal. It's going to be the polar areas are going to have the most room. So that's where the lone pairs would go. Okay. In this case, we're going to have 2 lone pairs. 2 lone pairs, again, are going to go equatorially. That means they're stuck here. So that's what the electronic geometry would look like. The molecular geometry, we never see the lone pair, so that's what it would look like. T-shaped. That looks like a T to me. And then if we had nothing equatorially except lone pairs, this is what the electronic geometry would look like. Molecular geometry would be linear. Okay, so the central atom has got 1, 2, 3, 4, 5 electron groups or electron domains. We're going to be using this bipyramidal geometry. Now let's go to 6. Here, the lone pair is going to go to the most room, which in the case of the octagonal is on the polar areas. So those are going to fill first with the lone pair. You get a lot of different kinds of pyramidals, 3-dimensional pyramids. In this case, we've got a square pyramidal. Now these are going to be in a chart. They're in a chart in your lab document, and you need to get used to using that chart. If you have 2 lone pairs and you have 6 electron domains, being the polarist, most area, that's where the lone pairs are going to go. So square planar going to be your molecular geometry. And these are the 2 pages that kind of run through. Now you need to be able to look at these charts and use them. Now on Thursday is your next test. So you're going to be allowed to use these for your tests. In fact, what I'll do is I'll just include it with the test. And your test is going to be in here, by the way, on Thursday as well. Okay. Now the problem with paper, it's 2-dimensional. In real life, everything is 3-dimensional or 4-dimensional, whatever. The main thing is, how do you represent 3-dimensional objects on 2-dimensional paper? And what they've come up with is a concept that allows you to visualize somewhat. Okay, so if we look at methane again. Methane is a tetrahedral, 3-dimensional tetrahedral. And how would I represent it using these triangular things? Okay, so one way to do it would be like this. a solid wedge instead of a straight line, that bond is going to come out of the page. And then conversely, going into the page, on the other side of the page, is going to be hatched or something other than solid. It depends on your book and worksheet how they represent it. These are going to be in the same plane as the paper. So this comes out at you, this goes in. This is very common. That was your question a while back. This is commonly used. Depends on the publisher, how they represent it. When you get into biochemical molecules, tend to be very complex and very three-dimensional. So they use these a lot. And again, the concept of the central atom is key to this whole Vesper. So the analysis is done per central atom. So in the case of the amino acid glycine here, we'd have 1, 2, 3, 4 analyses. Okay, so on the test, if I show you, that's the first test to do. Do the Lewis diagram. Second thing is how many central atoms are there? And you need to divide your workspace up into per central atom. And then go across and say how many electron domains are there? What's electronic geometry? What's bonded? What's not bonded? What's the molecular geometry? What's the angle? That kind of stuff. Per central atom. Now, when we look at polarity, there's there's central atom polarity, and then there's molecular polarity. When I say molecular polarity, that's of the overall molecule. Suspected spam, it says. Gee, should I take this? Has your spam has your spam calls increased lately? About the last 3 months, I've been getting a spam call almost every morning, like at 8:15. And it goes like 4 rings and then nothing. And there's no follow-up. Just such a freaking pain, I swear. All right. So when we can look at a So we've talked about the polarity of carbon dioxide. So number one here, if we look at the central atom, okay, we've got, that's going to be a polar complex. That's going to be a polar complex, but because they're the vectors direction are 180 degrees, they cancel. No polarity. We look at water. You have two vectors, and those don't cancel, hence the molecule is polar. But what happens if we have multiple central atoms? Then we have to look at the overall polarity of each central atom relative to one another within the molecule. Okay, in glycine, for example, we've got 4 central atoms. Each one of those is either going to be nonpolar or polar. Then you need to consider the overall polarity of the molecule. So whenever we have an oxygen with lone single bonded pairs, that's a very polar spot in that molecule. Likewise with nitrogen, not as much, because nitrogen has 1 lone pair, oxygen has 2 lone pairs. Okay, so here is a polar spot. Here is a very polar spot. What about this here in the middle here? Would that be polar? If we did the delta En, no, because the delta En for CH is 0.4 and the delta En for CC is 0. So the only polarity in this molecule or this central atom would be here. And we have this up here. We have a CC, which is going to be 0. We have a CO, which is going to be a little different than this CO, but polar. So this is going to be slightly polar. So overall, this molecule is going to be pretty polar because we've got a number of polar sites and a very non-polar site. The key is look for O's first. Look for oxygens first. Are they single bonded or double bonded? If they're single bonded, that's a very polar spot in that molecule. Okay, same for N. N is not as dramatic as oxygen, but it's still a polar spot. Second thing is to look at the symmetry. So those are the 2 main areas that'll easily allow you to determine polarity. Okay, the chances or likelihood of a molecule with a oxygen single bonds is extremely high. The reason for that is the shape of the single bonded oxygen is very arrow-like because of the lone pairs. And that distorts the shape a lot. It's not very symmetrical at all. So boom, as soon as you get oxygen in there, you're throwing in that pointy oxygen geometry. Makes it very hard to be symmetrical. And number two, is look at the molecule itself. Is the molecule itself symmetrical? If it's not symmetrical, polar. Now, nature likes symmetry. That's why when we studied electronic configurations, we looked at, remember we had the subshells being full or half, whatever. And when they're full, it was more stable. The reason for that is nature likes symmetry. When they're full, they're nicely balanced. When they're half full, they're nicely balanced. So again, symmetry comes in. I teach this for my intro class, my advanced class, this concept of symmetry. And there's a lot of calculations you can do and blah, blah, blah. All that ends up being the same place. Symmetry, and look for oxygen and nitrogen. Those two are big harbingers of a polar molecule. So, glycine. Does this have any chiral molecules in it? Huh? Am I putting you on the spot? Okay. This is the only amino acid that doesn't have a chiral center because of this guy here. Remember, it has 4 independent groups, and CH and CH are the same. So that automatically disqualifies it. So glycine is the only amino acid that's neither D or L. All the rest are D and L. So you guys need not know that. Just she's taken biochemistry, so it's always asked that. Okay, so just looking at this guy as a candidate, would this be a polar molecule? Well, is there an oxygen in there and a nitrogen? Yes. Single bonded, yes. So red flag. And then when you look at all the central atoms, most of them except one has some polarity to it. So it's a polar. Acids are polar because of this. Now, I'm going to give you another example, which is very different, but really the same. When you get into OChem, you don't have to draw the H's. When you get into biochemistry, you don't even have to draw the carbons. But if you're not in those classes, you got to draw the H's. Now there are 16 carbons here. I was going to do the 18 version, but I just got tired of doing the. Okay. Now this is a trick question. Is palminic acid polar or nonpolar? Who said polar? Why polar?
Because it's an acid.
I mean, this here,
It's not single bonded.
single bonded, right? So you know the answer, right? I hate to keep picking on you. Why don't you just, I know you know the answer, just, okay, everyone, what do you think? Is this a polar molecule? It's giant.
That part's polar, that part's not polar.
Good. It's neither. Because it's got a polarity part, and these are all very nonpolar. So what would this molecule be good for? Making ivory soap, for one. Remember a while back we talked about emulsifiers and soap. Soap has to have a polar part and a nonpolar part. Here we have it. Now this is called a fatty acid because whenever you have something called a triglyceride in your body, which is one of the measurements when you do a lipid panel, is they measure the amount of triglycerides, okay? And a triglyceride is made up of fatty acids. Fatty acids differ in the number of carbons and also in the number of double bonds. Depending on the source of the triglyceride, it'll have a varying amount of single and double bonds. The more single bonds it has, the less healthy it is. Pork, beef, chicken, got a lot of saturated fats. Things like vegetable oils, like olive oil, et cetera, has less single bonds and more double bonds. Okay, so if we wanted to make a soap from this, could come from pork, could come from lamb. There's a lot of sources of palminic acid, including vegetable sources. We would need to get rid of this to make it even more polar. Once we take off the H, like when we react this with sodium hydroxide, we'll end up with sodium. And I need to do a copy and paste because I don't want to do it over again. Okay, so this is called the either the sodium salt of palmitic acid or sodium palmate. Okay, this would foam up nicely. This would foam up nicely. It would get rid of, it would bind up fats because of the nonpolar end. It would bind up with water because of the very, very polar. Now, by taking the sodium salt, we've made this end even more polar. So it's really polar now, in contrast to this long nonpolar end. So emulsifiers, by definition, have to have one of each. It's like glue. ¿Cómo se dice? Pegadora? Yeah. And these are very common in our bodies. There's one called lecithin. That's what they use to make mayonnaise with. Lecithin is big time in egg yolks. So if you make a homemade egg yolk or homemade mayonnaise, you need to use an egg yolk. And the egg yolk supplies the emulsifier lecithin that keeps everything all mixed up. The oil and the vinegar that makes mayonnaise. When you make a vinaigrette, you can add a part of an egg yolk there that'll keep it emulsified, keep the egg, or keeps the oil and the water totally mixed. And all has to do with this polarity stuff. Now, we talked a little about vector addition. Okay, remember, vectors have both direction and magnitude or quantity. And to add them or subtract them, you've got to take apart its components. And then you add the components together, which gives you a net vector. The bottom line is, scope of this class, we're not going to get into how do you figure these. It has to do with a trigonometric function, define the X, Y, Z components, etc. The main thing is when you have vectors going in the same direction, they add. When you have vectors going in the opposite direction, they subtract. And if the quantity is the same, they become null, like carbon dioxide. That's the main thing. And that's all we're going to cover in vector addition. But the main thing is forces are vectors. Forces are vectors. When you take physics, you'll get that out the yin yang. Okay, where are we here? And this predicting the polarity of molecules again, take into consideration those two steps. Does it have an oxygen molecule or an action? Does it have an oxygen atom in there? And are they single bonded? Secondly, when you look at all the central atoms, are they mostly polar or mostly non-polar? And you have isolated areas as well. Yeah.
If you had a molecule that had like 4 central atoms and there were like 2 polar areas and 2 non-polar areas, would that cancel?
Remember our symmetry. Okay.
Oh,
So you've got the non-polars in the same area and the polars, and you've got it non-symmetrical.
but
So
let's say it was like symmetrical, then what would?
Well, you just got to look at them. Is each central atom vector going the same direction or opposite? If they're opposite, they kind of cancel. If they're going the same direction, they're going to add.
And it's polar.
Yeah.
So you have a net
Yeah.
vector. Okay.
And also is a molecule symmetric? Symmetry is a big deal in nature. It really is. It's we've mentioned this a number of times. Polarity affects solubility. The more polar the molecule, the more easily it's soluble in polar solvent like water. Like dissolves like. That's what they're getting at here. When you become an ionic component, it becomes very polar. Just like when we took that palminic acid and made it a sodium salt, an ionic acid. It became very, very, very polar. So this is the classical vinaigrette. We have some kind of a vegetable oil, and we have vinegar down here. Vinegar, 95% water, 5% acetic acid. You got the classic deal. You shake that up, and within 30 seconds, what does it do? Separates it back out. So you add something to make it an emulsion. Emulsions require emulsifiers. Sometimes they call them surfactants. You want something non-polar to bond to the oil, something polar to bond to the water, keeps them separated. And that can be things like mustard, could be various types of finely grated cheese, could be croutons. Lots of things act like emulsifiers. Sometimes they act like emulsifiers physically and others chemically, or a combination of the two. Okay, issues with the Lewis theory. One, it's two-dimensional, not three-dimensional. That's probably the biggest gaffe. And we haven't talked about para and diamagnetism yet. That has to do with whether the spin of the electrons are paired or not. For example, why is iron magnetic and some of these others not? If you look at the electronic configuration of iron, you've got a lot of unpaired electrons. Remember, those have spins. The spins are magnetic. So if you've got a lot of magnetic spins going in the same direction, they're building. If you have them paired, they cancel. So if everything's canceled, no magnetic tendencies. If everything is full but unpaired, it's magnetic. And there's everything in between. The valence bond theory is this VSEPR, valence shell electron pair repulsion, VSEPR. That's what the electronic geometries, molecular geometries. These are nice summaries of these approaches. Now, if we're looking at, we're going to have a hydrogen-hydrogen bond. Okay, that requires a single H and a single H as they come together because the single H does not have a full shell. We've got half. It wants to become like helium. So as it comes together, it becomes more and more stable to a point. And that point is when it gets too close, because then the electrons, instead of sharing, they start repulsing one another. And that's what this distance here is. And that determines the bond length. So this is an unstable situation because they're too close together. Those electrons now are repulsing one another. When they're just right distance-wise, that is the most stable. And this is potential energy now. The lower potential energy, more stable. Now, we're going to get into something called MO and AO theory, molecular orbital theory, atomic orbital theory. From quantum mechanics, the orbitals act like waves. So they have wave properties. So when you mix two waves together, you lose the original two waves and you make two new waves. And the way this works is oh, it's not, okay. So when you bring two atomic orbitals together, okay, so when you bring them together, the originals no longer exist. So what happens is you have a you have the new sets of waves. Those are called constructive and destructive. So when you add them together, it depends whether they're like this or like that. In fact, let me swap those. So the constructive wave builds a new wave. Notice as we go through here, it goes peak, trough, peak, peak, trough, peak. So those are in sync with one another. Hence, you build a constructive version of that. So the first peak is, assuming these are the same size, is going to be twice as high as individually, either one of those. And the trough, the low part, is going to be twice as deep. If you have a peak and a trough coming, what do you think those are going to do? Cancel. So you end up with almost nothing. That's the destructive wave. And if they're perfect, you end up with nothing. Who at home has a keyboard? Either one, piano, electronic. Okay. I'm really into piano stuff and music. So if you press a C and a G, I want you to go home and try this. Press the C. I'm going to use tonic C, and a perfect fifth of tonic C is G. So you go, ding, dong, and then press them together. What happens is there's no longer a C, no longer a G. There are two new waves. You hear the constructive one, and you don't hear the destructive one. Super easy to do. G and C, or any fifth, perfect fifth. You can do AE, a lot of different combos. But you can really hear the difference. Because when you press the C and the G, there's a totally harmonious new note you hear. You don't hear two notes, you hear one note. The other note you can't hear because it's destructive. It kind of cancels everything out. So try that at home. And do it fairly loud too, so you can really hear it. Now, when two atoms come together, they each have their own wave orbital. As they're coming together, we get the constructive and destructive wave formed as the molecular orbital. The molecular orbital is wave properties. The atomic orbitals have wave properties. So two waves come together, they form two new waves, constructive and destructive. Now in your worksheet, they want to know the hybridization. Hybridization starts at electron domains number 4, 5, and 6. So when you have 4, it's Sp3. And this goes back to, remember we had the S orbital and the 3 p orbitals. Those all come together to form 4 degenerate orbitals. The name of the new sets of orbital is called Sp3 because it's made of an S, 3 Ps. Now we can, that's a very common practice within molecules and atoms. If you have 5, it's Sp3D. And involves some of the D shells. When you have 6, it's Sp3D2. Those are just, I cough a lot here. Dizzy. So these are new sets of orbitals that have been becoming hybridized. The S's and the P's and the D's have mixed together. Now the number of orbitals hasn't changed. It's just the relative stabilities have changed. And this one we talked about when I showed you the hybridized. So if you do the electronic configuration for carbon, it ends up being this. 2 singletons mean it can bond twice. Carbon bonds 4 times. So the way to rationalize that is we have S&P or S&P hybridization and ends up with 4 singletons. And then we can continue that concept to 5 and 6 electron domains. Okay. The reason why we hybridize is for, where's the right word in here? Stability. Number 1. And number 2, we hybridize because it answers the question of molecular bond shapes. In other words, with carbon should bond twice if we did the classic, but it doesn't, it bonds 4 times. So the shape of the carbon molecule is different with the hybridized version versus the unhybridized version. So 2 things, stability, good old nature, and it helps us predict the shapes. Now, that's not to say that the old versions are around. They're just not as stable. It's not black or white. It's mostly the hybridized version, but you get a little of the old one thrown in as well. So oh, one other thing too is when we hybridize, sometimes we hybridize a little differently each time. As long as it's legal in terms of what we end up with. So for example, carbon can be hybridized 3 different ways. Tetrahedral, sp3, sp2, which is a double bond, sp is a triple bond. All are legitimate for the same reasons, stability and the shape of the overall molecule. Okay. So this would be the sp3 hybrid. And that's how we end up with a more stable carbon. And secondly, we can predict the shape of the carbon in sp3 hybridization because it takes 4 bonds. Okay, so if that's sp3 configuration, okay, so that's the standard configuration for carbon, right? Okay, so let's hybridize that. We already learned that sp3 hybridization looks like that. That's for a single carbon bond to something else, sp3. Okay, remember I said there are 2 other carbon hybridizations? Let's see what those look like. Now remember with hybridization, the P's are destabilized. Excuse me, the S's are destabilized and the P's are stabilized, okay? So these get stabilized. And this gets destabilized. All right, so now we're going to mix them up, the electrons. Okay, we have 4 electrons. Now, this is going to be the sp3. Let's look at the sp2. Now, what happens with the sp2 is it looks like this. Okay, so we have now between the sp2 and the sp3, which is the thing more stabilized? One on the right, but compared to sp3. That's right, and that's right. That's correct. Okay, so let me draw sp3 below here. Okay, so we've got sp2 and sp3, which is more stable.
Yes. two, just because it's got one electron in a low in a low, that seems more stable than that all in the higher.
Okay, sp2, what you're talking about, right?
Yeah.
And which of these electrons is more stable of the four?
S.
Okay, but there's no s now.
Oh, what's the one on top of that?
That's a sp2, which is equivalent to these two.
Oh, okay.
This is a pure p, by the way. This is not hybridized. Yeah.
Could it be Sp3 because they're both powerful? And also,
Yes. Okay, the overall energy of the sp3 is lower, average, than this one here, because you got that outlier there. That high p that was never hybridized is not all that stable compared to the rest of the electrons. So sp3 hybridization is more stable than sp2 because of this guy. Now remember, sp2 is for double bonds. sp3 is for single bonds. So which is more stable, single or double bonds? Single, because of sp3 hybridization. You got this, you don't have this outlier up here. Now, there's a name for that outlier. So not all electrons are created equal. Yeah.
Why would a single bond be more stable than a double bond?
Because on the average, these four are at the same level as this. Okay. So say this was 1, 1, 1, 2, this would be 1, 1, 1, 1. So what's the average down here? And what's the average up here? A little over 1, right?
But does it not have anything to do with like, this could be very wrong, I'm not sure. But I feel like breaking a double bond is harder than a single bond, so then I thought that it would be more stable. With it?
The concept is exactly right, except it's opposite.
Oh, really?
So to break a double bond is easier or harder? Easier, why? That's correct.
Is it because that energy level isn't
Yeah.
stable? Okay.
Because the 4 and the sp3 are more stable than the 3 and the 1. Now, when you get into organic chemistry and biochemistry, you'll find that's true. Double bonds are not as stable as single bonds, hence they react easier. They're not as stable. Let's go one step further. Okay, so an sp hybridization is a triple bond. So it has even more p outliers. So you have 3 versions. You have sp3, sp2, sp1. Which do you think is the most stable using the analogy of between the 2 and 3? Now this takes up like the first, you get this in the first or second week of OChem, this specifically. You remember those old days of bond hybridization stability? Just look at these diagrams here. Remember what makes the sp3 and the sp2 different in stability? That's right, exactly. Are they all created equal? sp3 is all degenerate. They're all equal, right? Are sp2 all equal? One is not. One is more unstable, And it was the original P. Now with this guy, not only have the original P, we have two original Ps. So using the analogy of the Sp3 and the Sp2, Sp2 being more unstable. What do you think about Sp? Stability-wise. It's either, that's right, and the reason is, yeah, the unhybridized Ps, you have more of them, the unhybridized Ps. So when you weld, anyone here weld? Use something called acetylene. Acetylene uses an acetylene gas, which is a triple bonded carbon. You think that's a very stable configuration? No. So it wants to become more stable by burning because it wants to take that triple bond and make it single bonds. Single bonds are more stable. So we want to go from triple to single. Doubles want to go from doubles to singles because of that P electron. So how many pi electrons does this have? 2, yeah. So these are pi, these are sigmas. Sigmas are very stable, pi's are not. So if we can convert pi's to singles, we have a more stable bond. So this is and this is really important when you get into biochemistry and organic chemistry. Now our bodies don't have any triple bonds. Why do you think that is? They're really unstable. And our bodies sit around for 70 or so years and kind of function okay. We throw in some triple bonded crap or some free radical crap, and we die sooner than 70 years because those things are not stable. Okay, how are we doing on time?
I heard once that triple bonded nitrogen was one of the most stable things.
Well, triple, I mean, okay, with nitrogen now, you've got different numbers of electrons running around. So it doesn't hybridize as much. Carbon is the one that hybridizes big time. And then silicon below it. Okay. Okay. I want to end this here. Here's the Sp2 we just talked about, where that would be the pi electrons. Sigma. Now this is what a double bond looks like. Okay, so you've got the C here with electrons around it. Got the oxygen here, same thing. Now, when the two P's of the Sp2 carbon and the Sp2, I mean the P on the oxygen come together, that's when we form the pi electrons. Okay, when the lower ones, the sigmas, come together, we form a sigma bonds. So in a double bond, you've got two kinds of bonds. You have a single, excuse me, you have a sigma and you have a pi. The one that breaks is the one that is most unstable. So which bond do you think breaks, the sigma or the pi? Pi, because it's made up of those high P electrons. Same with the triple, the two pi's break. the sigma stays intact because it's super stable. Okay. So when you have a double bond, you've got two kinds of electron bonds being done, one a pi and one a sigma. Okay, so I'm going to end this here. So we're going to go into the lab and I'm going to have a nice break. I've been talking the whole time. I need a break too. My throat is super dry. And I want to talk a little about getting into the configuration from your lab. We're going to be using the some of these 5 and 6 electron domain configurations. And I want to go over the test as well. Okay, yeah. This. At the end, we're going to get 4 tests and it's moves right along. We have 3 weeks left for the semester. So there'll be a test this week and then a test at the end. And then theoretically, they don't give me a lot of direction in this department. Most schools I've taught at for 1A, they give the American Chemical Society standardized test. It's multiple choice. And I don't know if they do that here or not. So I need to check, and that'll be your final. And it's multiple choice. It's given all over the nation, probably all over the world, to first year, first semester general chem students. Okay, and a lot of classes, they double and triple the value of that. It's just a regular test in my class. Because sometimes the verbiage is different. It's different than you're used to. And okay, anyway. All right, so you guys take a break. I will see you over in the lab in like 3:15, 15 minutes, okay? And you don't have to wear a lab coat. You will have to wear goggles. Oh, when I cough a lot, I get dizzy. All righty.